Okay, in this problem, we're going to look at the cost of production model. This is a cost minimization problem. And the thing about output, we have a production function here. We combine capital and labor using this technology. The technology being we multiply capital and labor and we take the square root and we get output. Now, why do we use square root capital times labor? Well, in the short run, we hold capital constant, and as L increases, Q will increase, but at a diminishing rate. Let me show you that. Okay, so if I got my production function here, right? I got Q equal to the square root of capital times labor, right? I can't graph that because I have three variables here, and I got a two-dimensional space over here. So what I'm going to do is I'm going to hold capital constant. If I hold capital constant at 49, let's do 9. Whoops, 9. If I hold capital constant at 9, you can see that as I add laborers, output rises, but it does so at a decreasing rate, right? And that makes sense. It makes sense because your capital is fixed in the short run. As you add more and more people to the production line gets increasingly crowded, and individual workers become less and less efficient or productive. Okay, so this is the law of diminishing marginal productivity. So that's why we assume this a functional form. We want to impose this idea, this assumption that as we add more labor, our output will go up, holding capital constant, but at a diminishing rate, at a decreasing rate, right? We want to formalize the assumption of diminishing marginal productivity, right? Now I could do the same thing with labor, right? If I held my labor constant at 9, and the only thing that's changing here is capital, right? And as I add capital, right, with a fixed amount of labor, again, I see diminishing marginal productivity, right? Okay, so that's the production function, right? One of the problems with it, this is a long run problem. One of the problems with this equation, again, I mentioned this before, is as capital or labor increase, output increases. So we need a three-dimensional graph of this production function, but we really can't do that on a laptop with decimals. We really can't do that. So what we're going to do instead is we're going to make the assumption that DeFara Pizza expects its future sales to be 50,000, right? So if we assume output is given at 50,000 per day, right? We want to build our business so that we meet that expected future demand, right? And so we're going to hold the quantity constant at 50,000. And then we're going to build our business based off this expected future production level of 50,000 pizzas per day, right? So if this is just a number by assumption, we can graph it in terms of K. We can solve it for K and then graph that in terms of L, right? And so that's what we're going to do here. These two are equivalent equations. If this one's true, this one's true, right? Mathematically. And the way I did it is I just squared both sides. So the left side becomes Q squared and the right side becomes K times L, right? And then I just divided by L. So that's how I went from this equation to that equation. I divided both sides by L, right? After I squared both sides. Now 50 squared, well, that's 2,500, right? That's 2,500. So all I'm doing is I'm plugging this 50,000 into that Q right there, right? And 50 times 50 is 2,500, right? And this graph here, this graph right here, is called an isoquant. And it's kind of called an isoquant because along this blue curve, we're holding output constant at $50,000. And you can see right here, labor is about 40, right? And capital is about 75. That combination of capital and labor will produce 50,000 pizzas per day by assumption, right? If I increase labor by 60 and I hold pizza production constant at 50,000, then I would only need about 42, 43 units of capital, right? To produce the 50,000 pizzas per day, right? If I further increase my labor to 120, I would only need about 20 or 18, maybe 18 units of capital to produce my 50,000 pizzas per day. If I increase my labor to 300, this is actually 300, right? 60, 120, 180, 240, 300. This is actually 300. If I increase my labor to 300, then I would only need about 9 units of capital to produce my 50,000 pizzas, right? So that's why this is called an isoquant. Iso meaning same and quant meaning quantity, right? So quantity is being held constant on this curve. And it's being held constant at what we think our demand will be in the future, right? Now down here, I'm making some assumptions. My capital cost $1,120 a day, and my pizza chefs, which are also called that just translates to pizza chef, is $280 a day, right? So this is my daily cost of capital. We'll call it rent. You know, you got to rent a building. And this is my wage, W, right? And we're going to use that information to complete this table. And then I got a model here. You can just modify it. So let's go ahead and open up the Desmos.com model. And I'll skinny it up a little bit. Now my output is 50, right? 50. The units are thousands of pizzas per day, right? But this right here means 50,000 pizzas, right? So that's my first assumption. My next assumption is the daily cost of capital, which is $11.20, right? And my last assumption is my wage, my hourly or my daily labor cost per pizza chef, right? I'm going to pay pizza chefs $280 a day, right? Then we're going to use this information to complete this table, right? Now, notice my labor in the first row is 25. So I'm going to reset my labor 25. Right? And I'm going to set my capital, the number of coal-fired pizza ovens, to 25. Yep. Let me zoom it in a little bit. Okay. So down here, this is W times L is my wage bill. L is the number of pizza chefs. And W is that wage we pay them per day. R is the unit cost of, or it's the rent, right? It's the cost of our capital on a daily basis. And K is our assumed value of capital. So when we multiply the expenditures on capital with the expenditures on labor, we get a cost of 35,000, right? That's how much my capital costs, or that's how much my production costs, right? Now remember, output is the square root of capital times labor. So down here, I got my labor and I got my capital, right? I'm going to flip these around. Got my capital, right? And I got my labor. 25 times 25, take the square root of that, that's 25. Okay. So my output is 25. Now I wanted to produce, I want to produce 50, right? Can I produce 50,000 pizzas a day with 25 pizza chefs and 25 coal-fired ovens? I can't, right? So 25, this is the deviation from expected. So this is 25 minus 50, right? 25 minus 50 is a negative 25. And 25,000 pizzas below what I expected to sell, right? Now, in row 2, I'm going to increase the number of pizza chefs to 100. So I'm going to change my L to 100. I got my coal-fire ovens still at 25. The cost of these two, of this capital labor ratio, the cost of this capital labor is 56,000. My costs are higher, right? My costs are higher. So I have the same number of pizza ovens, but I have 4 times as many labor. So my costs are obviously more, right? And this black line here, this black line is called an ISO cost line. It's called an ISO cost line. In the utility model that we did last week, we called it a budget line. But here's an ISO cost line. This point here costs the same amount as that point there, which costs the same amount as that point there, right? These 3 points, or any point in between these 3 points, cost the same for each bundle of capital and labor, right? Here we got 0 units of labor and 50 coal-fired ovens. Here we got 25 coal-fired ovens and 100 laborers. And here we got 200 laborers and no coal-fired ovens, right? So this line, if you calculate the cost at these 3 points, they're all going to be $56,000, right? I can change this to 0 and 50 to show you, right? Yeah. So the cost is 56,000. I get the same ISO cost line. I can change this to 200 and 0, right? I get the same ISO cost line, right? I get the same ISO cost line. Okay. So let me go back to 100 and 25. Okay. Now at 125, where am I at on this budget line? I'm right here, right? And notice that point is also on the ISO cost line, right? It's also on the ISO cost line. And I know that to be the case because capital times labor, square root, it produces 50 units of output, right? And I expect to sell 50,000 pizzas per day, right? So my deviation from expected sales is 0 here, right? Okay, now suppose I increase my capital from 25 pizza ovens to 100, right? What's going to happen here? So I'm going to increase this out to 100. Okay, now I got to move this in, right? Okay, so now we have a situation where my ISO cost line is a long ways away from the origin, right? And the ISO cost line intersects the isoquant in 2 different places, right? The cost of this is 140,000, right? So it's really high cost, right? Costs a lot of money. Now, this point and this point cost the same amount, right? $140,000. How much can we produce at this point with 21 units of labor and 120 units of capital? Well, we're only producing 50,000 pizzas a day, right? What happens if we hire 480 pizza workers and we only have 5 pizza ovens? Well, it's going to be very costly, right? It's going to be very costly, and it's not going to be efficient because we're going to have all these people crowded around. We're going to have almost 500 cooks crowded around about 5 coal-fired ovens. We're not going to be very productive. That's what costs so much, right? We're only producing 50,000 pizzas here. We're only producing 50,000 pizzas here. So we're definitely not minimizing our cost, right? Okay, and our output is 100, right? Our output is 100. Now, 100 is, when I take 100 minus what we expect to sell, if I take the 100, our production at this point with 100 coal-fired ovens and 100 pizza chefs, we're going to produce 100 pizzas a day, but we only expect to sell 50,000. So 100 minus 50,000 is 50,000, or 50,000, right? Yeah. So we've overbuilt, haven't we? We've overexpanded our operation. We have too many coal-fired ovens, right? We're making too much pizza. We're not efficient. Our costs are too high, right? Our costs are too high. So if we have 100 coal-fired ovens, what do we got to do? We got to reduce our number of pizza chefs to what? If we have 0 pizza chefs and we have 100 units of capital, we're going to produce no pizza and it's going to cost $112,000. See that? So we can't even meet demand. We can't cut labor enough. If this is what we built out, right? If this is what we build out, it's going to cost a lot more, right, than having 100 pizza chefs and 25 coal-fired ovens. So this represents a really big problem, right? A lot of times businesses get in a situation where they overexpand too quickly, and then they're in this situation where their costs are way too high, right? And then they got to liquidate assets, right? We can call that malinvestment. So this would be a malinvestment, right? To get 50 units of output, we'd have to hire what? 25 pizza chefs. So we'd have 25 pizza chefs operating 100 pizza ovens, right? We're way over capacity. And that cost is dramatic, right? That cost is dramatic. Okay, so use the 3 scenarios. Let me go back to our the situation where our costs are minimized, right? So let me go back here to, we're going to flip this around. We're going to hire 100 pizza chefs and we're going to have 25. If we have 20, we're not able to make, if we only have 27s, we're not able to make the 50,000 per day, right? So if we go to 22, we're getting close, right? We're only producing 46,904 pizzas a day, right? If I keep adding the pizza oven, I'm getting closer and closer and closer to the 50,000 I need to make, right, a day to meet our demand. Okay, now we're really close, right? We're really close to meeting our demand. So if we get to 25, now we can meet our demand, right? So if we have 100 laborers and 25 pizza ovens, we can make our 50,000 pizzas per day at a cost of $56,000, right? Okay. So use the 3 scenarios above to answer the following questions. Tafaro pizza costs are lowest when it acquires what? 25 coal-fired pizza ovens and it hires 25 pizza chefs. But doing so means it can expect 25,000 lost sales per day. 25 lost sales per day. 25,000 lost sales if it does that, right? Its production costs are highest in the 3 different scenarios. There's infinite many scenarios here, so this is definitely not the highest cost, right? its production costs are the highest when it acquires 100 coal-fired pizza ovens and hires 100 pizza chefs. In doing so, it'll make 50,000 pizzas too many. 50,000 pizzas too many, right? And you can see here that our budget line is way out here, right? Our budget line is way out here. Our ISO cost line is way out here, I should say. ISO cost line, right? So in this situation, once you have the ovens, once you have these ovens and you're overproducing, what are you going to do? You're going to scale back. Well, you can't really scale back on your capital. What you can do is you can hire fewer workers, right? You're going to have a high cost, right? Acquiring 25 coal-fire ovens and hiring 100 pizza chefs minimizes its cost of producing 50,000 pizzas, right? And when I hit enter here, you're going to see optimal solution here, right? So this is the optimal solution. This is the cost minimizing level of capital and labor. Capital is 25 and labor is 100, right? At that point. And our ISO cost line just touches our ISO quant. ISO cost is same cost along the line. ISO quant is the same quantity along the line, right? So we just touch that right there, right? Okay, now a survey of pizza industry analysts forecast the hourly cost of coal-fired ovens to fall. That drop in cost works out to $777.78 per day. So I'm going to do this. I'm going to copy that, and I'm going to come over here, and I'm going to change this value here. Now, I'm going to paste it by doing Control V. Now, watch what happens to my ISO cost line when I replace, when I lower the daily rent of our capital. Our line rotated, right? Why is that? Remember, the ISO cost line has a slope. Where's it at? Right here. Our ISO cost line has a slope equal to the wage divided by the daily rent. The daily wage divided by the daily rent. My rent went down, which caused the slope or this fraction to go up in value. So my slope increased. Now, if I zoom in on this situation, you can see that my ISO cost line, the black one, now touches the ISO quant in two places, right? What does that mean? Well, I can reduce my capital or my labor a little bit to lower cost, right? So as a result, DeFara Pizza acquires 30 coal-fired ovens and hires 83 pizzaleros, right? So I'm adjusting over, if this is the case over the long run, maybe this is plan A, right? Right? This is plan A. We want 100 pizza chefs, 25 coal-fired ovens if this information doesn't change, right? And we expect to sell 50,000 pizzas a day, right? This could be plan A, but plan B could be what? Well, maybe the price, this is a what if analysis. What if the price of pizza ovens drops, right? Maybe it drops to 77.78 per day, right? So we need a plan B. What is our plan B? Our plan B would be to acquire 30 coal-fired ovens and hire 83 pizzaleros, whatever that, however you pronounce that, pizza chefs, right? So we're going to change this to 30, and we're going to change pizza chefs to 83. Now we get a situation where our output, if we round it to 2 decimal places, is pretty close to 50, right? If I do 83.4, I get more than 50. If I do 83.3, I get just under 50, right? So it's if I round this to 2 decimal places, I get 50. My output will be 50, rounded to 0 decimal places. If my labor is 83 and my capital is 30. So my output, my production level will be equal to 50 pizzas per year. My cost will have gone down. See that? My costs have gone down. I'm going to hit Control C. If you have a PC, Control C. If you have a Mac, Command C. My costs have gone down, right? I'll put it in 2 decimal places. So the lower price of capital results in cost savings, right? Which makes sense, right? And notice what my new optimal solution would be. A is if capital doesn't change in price. Red, or in our what if analysis, shows you what we would need in terms of capital if the price of capital goes down, right? So we get fewer labor, we're demanding fewer laborers, and we're demanding more pizza ovens, right? We're demanding more pizza ovens. So the decline in the price of coal-fired pizza ovens, right? When the price of coal-fired pizza ovens falls, we demand more coal-fired pizza ovens, right? We demand more, not more chefs, not demand less ovens. We demand more ovens, right? We demand more ovens. So this is the law of demand, right? When the price of coal-fired ovens goes down, we're going to hire more ovens. We're going to acquire more ovens, right? We're going to substitute from labor to ovens. Maybe these ovens are automated, right? Maybe they're automated. And then we hit submit, see if we're done. Okay. And the way you'd graph, or the way you'd label this, this would be capital. This would be labor. This would be Q equal 50. This blue line would be cost, C, equal 56,000. This red line would be cost equal to 46,573, right? And then our optimal solution here, we started out with 100 laborers and 25 units of capital. We ended up with 30 units of capital and 83 pizza chefs, right?